Okay, hi everyone. So I am Maria Cristal Rose T. Balagulan, a first year BS Pharmacy from Section B. So today I will be discussing about the first reaction of alkenes and alkynes, which is hydrogenation. So in hydrogenation, there is an addition of hydrogen. Diba? From the name hydrogenation, there is an involvement of hydrogen. Let's not forget that. So in alkenes, let's go over first with alkenes. Okay, so we all know that alkenes have unsaturated hydrocarbons with at least one carbon to carbon double bond. Anong double bond man? Okay, from the name itself, alkene, E-N-E, double bond dyan na siya always. Mao dyan na iya ha. Di dyan na mabago. So, unsaon man pag-react sa alkenes nigdungag ni hydrogen? So, ang generic niyang structure is ngun ani. Let's give you an example na lang agad-agad. Sa ethene. Sa ethene, we have two carbons. And in, it refers to double bond. Double bond na. Okay, so kung i-drawing na nato. So, ang general structure jud sa ilang process is like this. Ano diba? Ano siya H, ano siya H. Then, additional nga hydrogen. So, after that, naada ng ang hydrogen. So, naay musulod si catalyst. In this scenario, PD. Pwede ka magamit og PD or NI, up to you. Pero let's use PD on this scenario. So, ang catalyst, iyahang function is to speed up the reaction of alkenes in connection of addition of hydrogen. Ayan na siya. Mao na siya. Mao na yung makapaspas para mo react dayon dito. So, ang hydrogen sa hydrocarbons nga unsaturated. So, may tabuan ni, mabroken siya. Kaning double bond, mabroken na siya. Ang may tabo, if mabroken, mawala ang isa, then, mabago ang yung structure. Then, malahin na po yung name. So, ano siya. Let's say, connected rin eh. Maingon ani siya. Single bond, then, i-copy na to ang hydrogen nga naadi-ari nila. Here, each carbon of ethene has 2 hydrogen. Since double bond naman siya. So, let's copy the 4 hydrogens. And here, put here. Now, let's not forget to add H2 or the hydrogens. Duha ni siya ka hydrogens mo ng H sub 2. So, yung structure jud is like this. H to H. So, para ma-add siya diri, magdungag tag duha ka linya. H to H. So, maingon ani siya. So, from ethene, mahimo siya ethane. Hindi siya ma-right. Ethane. And ethane refers to a single bonded carbon to carbon single bond. Ano na siya? Carbon to carbon single bond ng ane. It's like ane. Yang ane, carbon to carbon double bond. O, dyan na siya, ane. Okay, so let's move on to alkyne. Okay, so may tabuan niya. We all know that alkyne is also unsaturated hydrocarbons with at least one carbon to carbon triple bond. So, ganun triple bond man, kay ang alkyne ends with YNE, which refers rather to triple bond. Gananap siya. Di po na siya pwede ma-change kay ane is to single, ene is to double, and yne is to triple. Let's remember that always, Jude. Okay, so since triple bond man siya, so let's use the easiest example, ethane. So in ethane, we have 2 carbons. Then it has triple bond na letter T na triple bond. So, saan man nato pag-organize? So, we need 2 carbons with triple bond. And then, since triple bond na siya tulo ka atom, we only need 1 hydrogen each carbon to make it 4. Kaya mao man dyan ang constant nga atom nga needed sa carbon. So, H to H. Karon, we're going to add the H2, or in structural form, H to H, bali duha ka hydrogen. Then catalyst will then react to it. Anang mahitabo niya, maguba ang kaninga bond, mahimo na siyang duha na lang. So, mahimo siyang ani, ana. So, since double bond na lang man siya, so ang kailangan sa kaning carbon is 2 hydrogen each. And perfect ni kinamatay addition para makomplete ang 4 atoms. So, nadiri ang original nga hydrogen, nadiri, then kanina pod, ari na pod. Mao na siya. Then, we're going to add this here at the bottom. Well, pwede raman biskan asa narana nimo. Pwede po diri dapita, diri sa kilid, ana. Pero, dara sa ubos, aron limpyo tanawon. Okay. So, 4 na siya. 1, 2, 3, 4. 1, 2, 3, 4. So, mauna na siya. From ethine to ethene. Unya, kay maubos pa man nato ang ethene into single bond. So, ang bahato na po na may tabo nga addition of hydrogen. Yani, let's change color. Another H2 na po. So, anak na sa siya. H to H na po na. Doon na po na hydrogen ang idungag. So, ang may tabo sa structure is, instead of double bond, mas single bond na siya. And then we are going to copy the 4 hydrogens here sa ethene, which is original na niya. May mo siya original kay ato naman pong himuon og ethane. Okay. So now, i-add naman po ni natong duha ka hydrogen nga gidungag na sad. So, mapadung na siya sa kiliran. Diri na siya. Ngayon na siyang ani. So, 1, 2, 3, 4. 1, 2, 3, 4. Ay, 1, 2, 3, 4. Okay. So, kompleto na siya. That's it na. Ethane. So, kung mangutana mo, giunsa man pagka-broken sa bond, giunsa pagka-guba. So, yan ani rin siya, guys. So, balik ta sa ethane kaganiha. Manani, di ba ang structural form sa ethane is double, carbon to carbon, double bond. So, naa siya duha ka hydrogen each. Harada na ito na ibutang. And then, mag-add man tag H to H. So, H to H na, guys. So, ang mahitabo, wait. Ang mahitabo, ang kaning H to H nga dash, mapadulong diri. Nya ang kaning isa ka linya gikan sa double bond, mapadulong diri. Unsa may pasabot nimo sa mapadulong diri ang linya. So, ang may tabo, let's erase it. Ay, magdungag na lang. Ang kaning nga linya, mabutang diri So, maana na siya. Nya ang kaning nga linya, mapadulong na ni si diri. So, maana na siya. So, perfect na natay duha ka linya nga blanco nga kailangan butngan natog hydrogen. So, mao na atong kabutngan sa hydrogen. So, mawala na tong double bond, may mo siyang single bond. Mawala na po ning linya tunga sa H. May tabo kay ma-H na sila. So, from ethene to ethane. Nana na siya ka-simple. And as for the alkyne, which is triple bond siya. Same thought ra gyapon, but I'll still show you how it happened. Okay. So, naana sila tagsa nga hydrogen each carbon if triple bond. So, now, we have H to H. Additional na po na. Hydrogenation na po na. So, ang mahitabo, ang kaning dash, mapadong na po diri. Ang isa nga linya, maguba, mapadulong diri. Gets na mo sa point nako? So, naanap ang kaning nga linya, mapadulong diri. Mugama na siya bagong linya. Ari na pud, kanina pud diri. So, i-erase na to. Kay naguba naman ang linya, naguba naman ang bond. Ibalhin na nato ang duha ka hydrogen diri sa bagong nga mga linya. Wait, sorry. Diri nga bagong linya. So, di ba? May mo siyang ethene from ethine. Diba? Nahimo siyang ana. So, since ethene pa man na siya, di pa man na siyang smallest structure, jud, di pa na kayo siya saturated. Kaning ethene, mahimo na po siyang ethane. By adding another 2 hydrogen. Mao na siya ang naitabo diri dapitan na akong gi-explain kaganiha kani siya. So, it ended up nga nahimo siya ethane, from ethine to ethane, from ethene to ethane. Oh. Yun ana siya, guys. So, That's all for hydrogenation. Let us proceed to another reaction of alkenes and alkynes. So that's all. Thank you.
Hello everyone, I am Darajay Davinido, first year BS Pharmacy. Today, I'll be discussing the halogenation of alkenes. So, what is halogenation of alkenes? Halogenation of alkenes is a chemical reaction in organic chemistry involving the addition of halogens like chlorine, bromine, or iodine. Across the carbon double bond, this reaction is characterized by its high radioselectivity and stereospecificity, making it a valuable tool for synthesizing various halogenated compounds. So, mechanism. The mechanism for halogenation of alkenes involves an electrophilic addition reaction where a halogen attacks the pi bond of the alkene, forming a cyclic halonium ion intermediate which then undergoes a backside attack by a halide ion to yield a vicinal dihalide product. The halogenation of alkenes proceeds through a concerted mechanism, meaning the bond breaking and bond formation occur simultaneously. The pi electrons of the alkene act as nucleophile, attacking the electrophilic halogen molecule. This leads to the formation of a cyclic halonium ion, intermediate bromium or chromium ion, depending on the halogen used. This intermediate is then attacked by a halide ion from the solvent or excess halogen, resulting in the formation of a vicinal dihalide. The mechanism for halogenation of alkenes involves an electrophilic addition reaction where a halogen attacks the pi bond of the alkene, forming a cyclic halonium ion intermediate which then undergoes a backside attack by a halide ion to yield a vicinal dihalide product. The halogen molecule attacks the alkene, forming a cyclic halonium ion. This intermediate is a three-membered ring containing a halogen atom and two carbon atoms. The halonium ion is highly reactive due to the strain in the three-membered ring. The halonium ion is then attacked by a halide ion from the halogen molecule in a nucleophilic attack. The halide ion opens the halonium ring, leading the formation of a dihaloalkene. The reaction is stereospecific, meaning the stereochemistry of the starting alkene dictates the stereochemistry of the product. If the starting alkene is cis, the product will be a racemic mixture of erythrodiastereomers. If the starting alkene is trans, the product will be a racemic mixture of triodiastereomers. This is due to the anti-addition of the halogens across the double bond. This means that the two halogen atoms add to opposite sides of the double bond. This is because the nucleophilic attack at the halide ion on the halonium ion occurs from the backside opposite to the halonium ion's bond to the carbon atom. Factors affecting halogenation. Number one is halogen. The reactivity of the halogen influences the reaction rate. Bromine is more reactive than the chlorine and iodine is the least reactive. In alkene structure, the structure of the alkene affects the rate and radiochemistry of the reaction, and for example, more substituted alkenes are more reactive. In solvent, the reaction rate and stereochemistry can be influenced by the solvent used. Halogenation of alkenes is generally not radioselective, meaning that the addition of halogens occurs equally across both carbons of the double bond, regardless of the substitution pattern. However, in cases where there is significant difference in the substitution pattern, Markovnikov's rule may be slightly favored, but this is not a strong effect. Halogenation of alkenes has various applications in organic synthesis, including synthesis of haloalkenes. This reaction is a key step in the synthesis of many important haloalkene compounds. And next, the preparation of vicinal dihalides. The reaction yields vicinal dihalides, which are useful intermediates in various organic reactions. And the last one is polymerization. Halogenation is used in the polymerization of alkenes to produce polymers like polyvinyl chloride or PVC. In conclusion, halogenation of alkenes is a fundamental reaction in organic chemistry with significant synthetic utility. Its concerted mechanism, stereospecificity, and relative lack of radioselectivity make it a predictable and reliable tool for the synthesis of a wide range of halogenated compounds. Further research into the reaction conditions and catalytic variations continues to expand its applications in organic synthesis. That's all for halogenation of alkenes, and then let's proceed to another reactions of alkenes and alkynes.
Good day everyone, I am Rochelle Baay and today I will be discussing the halogenation of alkynes, which is an important chemical reaction in organic chemistry. So this reaction involves the addition of halogen atoms to alkynes, resulting in the formation of dihaloalkenes or tetrahaloalkanes. So now let us first understand what is alkynes. So alkynes are hydrocarbons containing at least one carbon-to-carbon triple bond. This triple bond is composed of one sigma bond and two pi bonds. The presence of these pi bonds makes alkynes unsaturated, meaning they can undergo addition reactions. Compared to alkenes, alkynes generally react more slowly with electrophiles due to the higher electron density of the triple bond. However, under appropriate conditions, they readily participate in addition reaction. So now let us also understand what is halogenation. So halogenation is an addition reaction where a diatomic halogen molecule adds across a multiple bond, in this case the alkyne's triple bond. The reaction proceeds via an electrophilic addition mechanism. The halogen molecule acts as an electrophile attracted to the electron-rich pi bonds of the alkyne. This reaction is a fundamental transformation in organic chemistry, allowing for the introduction of halogens which can serve as versatile functional groups for further reaction. So, the halogenation of alkynes is the addition of halogens to an alkyne, leading to the formation of dihaloalkenes or tetrahaloalkanes. This reaction occurs through an electrophilic addition mechanism where the pi electrons of the alkyne act as a nucleophile and attack the electrophilic halogen molecule. So there are two halogenation reactions of alkyne. First is the addition of one equivalent of halogen, which is the partial halogenation that forms a dihaloalkene, or the major product is trans. And the second is the addition of excess halogen, which is the complete halogenation, and it forms a tetrahaloalkane or the fully saturated. So the first reaction mechanism is the addition of one equivalent of halogen. It is when an alkyne reacts with 1 mole of a halogen, the triple bond is converted into a double bond, forming a dihaloalkene. So the halogen atoms are added across the double bond in an anti-addition manner, meaning they can attach on opposite sides. So the example is the ethine reacts with bromine to form 1,2-dibromoethene. So the product is a trans-dihaloalkene due to an anti-addition of halogen atoms. And the second reaction mechanism is the addition of two equivalents of halogen. It is when an alkyne reacts with one excess halogen, the double bond undergoes another halogenation reaction, resulting in a formation of tetrahaloalkane, a saturated compound with 4 halogen atoms attached. So, the example is the ethine reacts with excess bromine to form 1,1,2,2-tetrabromoethane. So, the final product is fully saturated tetrahaloalkane. So, these are the examples of alkyne halogenation. The first example is the bromination of acetylene. So the first structure illustrates that one equivalent of bromine results in trans 1,2-dibromoethene. And the second structure also illustrates that the excess of bromine leads to 1,1,2,2-tetrabromoethene. And the second example is the bromination of 2-butane. And the second example is the bromination of 2-butane. So the first structure, which is the trans dibromotobutene forms with one equivalent of bromine. And the second structure, which is the 2233 tetrabromobutane, and the second structure, which is the 2233 tetrabromobutane, illustrates that it forms when excess bromine is used. So in terms of application, alkyne halogenation produces halogenated intermediates for further chemical transformation when applied to organic synthesis. And in pharmaceutical industry, it is used in the production of drug precursors and active pharmaceutical ingredients. In conclusion, the halogenation of alkynes is a fundamental electrophilic addition reaction that introduces halogen atoms into organic molecules. The reaction proceeds via a halonium ion intermediate following an anti-addition mechanism, leading to trans-dihaloalkenes when one equivalent of halogen is used and tetrahaloalkanes when excess halogen is added. This reaction has significant applications in organic synthesis, pharmaceuticals, and material science. That's all, and thank you for listening.
Hello, good day everyone. My name is Julianne Bompat from Section B First Year Pharmacy. So let's talk about hydration of an alkene. Hydration, you automatically think about water. So our topic for today is the addition of water to an alkene. There are two things that I want you to know. So first, you have to have an acid, a strong one in fact, and typically we're going to use a sulfuric acid in order to induce this hydration, adding the water to the alkene. And the second thing that I want to point out is the Markovnikov's rule. So Markovnikov's rule tells us that hydrogen is going to always go to the carbon that's less substituted. So which means the carbon that has the most hydrogens. So let's move on to the basic formula. So you're going to have the alkene plus water, and when it breaks apart, the hydrogen will go on one carbon when the double bond breaks, and the hydroxide will go on another carbon when that double bond breaks. So here I've got ethane with my water in the presence of the strong acid, sulfuric acid. So that double bond breaks the hydrogen goes to one carbon and the hydrogen goes to the alcohol group, that OH goes to another carbon. So I wrote here just a reminder that hydrogen will always go to the carbon that has the most hydrogens in this case. So let's do some problems. So number one, we've got methyl. This is actually going to be 1, 2, 3 carbons. So we've got the prop since it's 3, and this would be the 1 propane. We add the water to it in the presence of that strong acid, the sulfuric acid. So the double bond breaks and the hydrogen is going to go to this first carbon because that carbon is bonded to two hydrogens. The alcohol will go to the second carbon because this carbon is bonded to one hydrogen and one carbon. So this right here is called less substituted. It has more hydrogens. It's not have substituted with carbons. So over here, the alcohol goes to the carbon that was bonded to a carbon, and this hydrogen goes to the carbon that had more hydrogens. This carbon had two, that carbon had only one hydrogen, so it goes to the one with the most hydrogens. So let's move on to number 2. We have a methyl group with the cyclohexene. So a carbon double bond that's going to break when we add the water in the presence of the strong acid, sulfuric acid. So the alcohol is going to go to the carbon that has the fewest hydrogens, that has the most carbons. So notice that conjunction that carbon is bonded to 1, 2, 3 carbons. So the OH goes to that carbon that had the bond with 1, 2, 3 carbons. The hydrogen would go down here. The hydrogen will come right here, but remember we don't have to draw hydrogens. So this carbon at this conjunction is only bonded to 2 hydrogens. It's bonded here 2 carbons, 1, 2, so the hydrogen goes here. This carbon is bonded to 3. This carbon's bonded to 2, so the hydrogen goes here. And remember that hydrogen, there's all that this hydrogen, there's already another hydrogen here. So now there's 2 hydrogens, so now you have 2 hydrogens together instead of just 1. So let's proceed to number 3, the skeletal structure. So we've got our 1, 2, 3, 4 carbons. There's the double bond. Add the water in the presence of that strong acid, sulfuric acid. This is going to break. So when that breaks, the alcohol will go here or here. So in this case, it doesn't matter either one because these carbons bonded to 1, 2 carbons. That carbons bonded to 1, 2 carbons. So you could write it either way. You could put the OH here or the OH here. So let's move on to number 4. We have 4 carbons but the double bond has moved. So this would be like a 2 butene and this one is 1 butene. So that double bond breaks when we add the water in the presence of the strong acid, sulfuric acid. And as always, the OH go to the carbon that has the most carbons bonded to it. Or you could see the hydrogens going to go to the carbon with the most hydrogens. So we just draw this out. So you're going to have this CH3 right here, a CH2, and this you got the carbon double bond here to a carbon. There's your 2 hydrogens. This has 1 hydrogen on it. That carbon has 1 hydrogen. So this carbon has 2 hydrogens. This carbon is only 1 bonded to 1 carbon, so that carbon's bonded to 2 carbons. So where does the alcohol go? So the alcohol is going to go on that second carbon. It's going to go when this breaks. So let me show you when this breaks. The alcohol will go on that and this carbon gets the hydrogen. So the carbon with more hydrogens. So that's it. Thank you everyone. I hope that was helpful.
In this video, we will be looking at the hydration reactions and what hydration reactions are. Then, we will looking at the mechanism for alkene hydrations. And we'll also talk about what products are produced from the hydrations of alkene. So, hydrations refers to additions of reactions which involves the additions of water across a double or triple bond. And it is important to note that we are adding a water into unsaturated hydrocarbon because they have a greater reactivity as a result for a larger electron density in these bands. The derivations of alkene will form as a alcohol. However, the derivations of alkane will form either a ketone or an aldehyde. So, as we previously mentioned, alkane are a form of unsaturated hydrocarbon and they are engaged in addition reactions because of the presence of an electron dense triple band. Because of this characteristic triple bonds which is present in alkane always cause strong nucleophile. This means that they seek out positive charge that exists in nuclei, and here we can see the characteristics CC triple bonds which exist in this alkane propane. So we'll be looking at two methods of algone hydrations with the formations of ketone and aldehyde. First, we'll look at the formations of ketone as a result of alkane hydration. In the first step, there's a nucleophilic attack from the triple bonds onto a hydrogen ion which is produced in the solutions as a result of the dissociations of an acid catalyst. As a result, we end up with the formations of electrophilic carbocations in the 2 position. In the next step, water is now nucleophile, and as the result, the water will engage in nucleophilic attack on the carbocations that exist in 2 position. And as the result, it will form a positively charged oxonium ion. From there, hydroxide presumably formed from a base catalyst deprotonates the unstable oxonium intermediate. As the result, will form an enol intermediate as well as regenerating the catalyst. From here, the undergo intermediate can then undergo tautomerization in order to stabilize its bond. Here we have the movement of the shift of this double bond into this position. Here, in order to form a carbonyl compound, the reason why this is more stable is because oxygen is more electronegative than the adjacent carbon that exists on the enol, which means that it has a better ability to absorb the electrons density and stabilize the double bond. So finally, we still have an extra hydrogen that is attached on the carbonyl, so this then deprotonates and will end up with the formations of ketone. Now, let's look at the formations of aldehyde as a result of alkaline hydration. We revisit step 1 to see what is the case for the formations of aldehyde. In step 1 really occurs in the same way in the electron-dense triple bonds engages the nucleophilic attack of the H+. This is similar to what we saw in step 1 for the hydration's mechanism that forms a ketone and that its end up formations of carbocations intermediate. However, let's compare this one with the one for ketone. We notice that the carbocations is now on the 1 position, whereas previously we saw that is formed on the 2 position. This is what going to be significant about the formations of the aldehyde. In the same way that occurs previously, the water is going to have a nucleophilic attack on the carbocations in the 1 position. In order to form this oxonium ion intermediate, which is then deprotonates again to form an enol, which is then tautomerized in order to form a carbonyl compound and deprotonates, now forming an aldehyde. So, to summarize, we know that the hydrations of alkane will produce either a ketone or an aldehyde. Ketone, however, are formed as a major product, while an aldehyde are formed as a minor product. A major modern product are detected by Markovnikov rules.
Topic for today is hydrohalogenation alkene. So our topic for today is hydrohalogenation alkene. So introduction is hydrohalogenation of alkenes is the addition of hydrogen halides or the, where X is equals to chloride, bromine, and iodide to alkenes, converting the double bond into a halogenated single bond. Below is a detailed explanation, the reaction overview. So the reactants is alkene and hydrogen halide. For example, it's hydrochloric acid and hydrogen bromide. The product is alkyl halide. So the radioselectivity follows the Markovnikov rules. It means that the hydrogen atoms adds to the more carbon with more hydrogen and the halogen adds to the more substitute carbon. So these are the mechanisms. Step 1 is protonation. The nucleophilic N electrons of the alkene attack the electrophilic hydrogen in HX, breaking the double bond hydrogen, adds to the less substitute carbon atom, forming a carbocation intermediate on the more substituted carbon 1. Step 2 is halide attack. The negatively charged halide ion attacks the carbonation, forming a new carbon X bond. So these are the key features. Regioselectivity is a halogen attacks to the more substitute carbon due to carbonation stability or the Markovnikov's rule. Second is carbocation rearrangement. If a more stable carbocation can form, so example is via via hydride or methyl shifts or the arrangement occur. Last is reaction conditions typically perform in inert solvents. So the energy profile. The action involves two transition states and one carbocation intermediate. Their protonation step is rate determining due to high activation energy too. Anti-Markovnikov addition in the presence of peroxides or ROOR and the hydrogen bromide can add anti-Markovnikov where bromine attached to the last substitute carbon due to radical mechanism. So this is the diagram. Below is a simplified diagram of hydrohalogenation. So alkene plus HX is to alkene halide mechanism. So number one is H minus X is to H plus plus X minus. So the double bond form into carbon and a plus with hydrogen carbon. So number three is carbon plus X is equals to alkyl halide. So example reaction is to for propene reacting with hydrochloric acid. So the step one is protonation forms with CH3 minus CH plus minus CH2. Step 2 is chloride attacks CH3 minus CH plus CH2 yielding CH3 minus CHCl minus CH3. So the hydrohalogenation is widely used in organic synthesis for preparing haloalkenes which serve as intermediate in further chemical transformation. So these are the examples of hydrogenation of alkenes. There are three examples of the hydrogenation reactants complete with diagram and explanation. So the example number one is the propane plus hydrogen bromide. So the image illustrates two different reaction mechanism. First is the mechanism of alkene hydrohalogenation. This shows that the reaction of alkene bromine to the double of bond of alkene attacks to the hydrogen of hydrogen bromide. This forms the carbonation of intermediate. Then the bromide ion attacks the carbonation, resulting addition of hydrogen and bromide across the double bond. So this is the final. And number two is a possible mechanism of alkene halogenation. So this shows the reaction of alkene with bromide, 2 carbomide, and the double bond of the alkene attacks of the one of the bromine atoms, forming a bromium ion intermediate. Then the bromide ion attacks to the bromine ion, leading to the addition of 2 bromine ion across the double bond. So that is the example 1. So in addition, the reaction of propane plus hydrogen bromide, propane reacts with hydrogen bromide to form 2 bromopropane as the major product. So, mo na siya ang major product sa bromopropane. And the mechanism is, step 1 is the double band. The double band attacks the hydrogen from the hydrogen bromine, forming a carbonation of the more substituted carbon. So, step 2 is bromine attacks to the carbonation, forming the product. So, muna siya ang product. So, example number 2 is the butane, but1 in plus HCl. So, the reaction of but1 in with hydrochloric acid in hydrogenation follows the Markovnikov rule. The hydrogen atom adds the carbon with more hydrogen substituents, and the chlorine atom adds the more substituent carbon. The result in the formation is 2-chlorobutane as the major product. So, money a major product. So, number 1 is starting the structure. This one. Where is it? This one. And then, yes, and the final product is 2-chlorobutane. So here's an additional information. So the reaction of but1 in plus hydrochloric acid is but1 in reacts with hydrochloric acid to form 2-chlorobutane as the major product. So its mechanism is, step 1, protonation of double bond forms a secondary carbocation. And the step 2 is the chlorine attacks the carbonation. So the final product is 2-chlorobutane. So the example number 3 is the hydrohalogenation of cyclohexane with hydrogen iodine. Follows the Markovnikov's rule. The hydrogen atom adds the carbon with more hydrogen substituents, and iodine attacks to the more substituent carbon. This reaction produces idiocyclohexane as the major product. So, so the reaction of the cyclohexane plus hydrogen ion is that cyclohexane reacts with hydrogen ion to form idocyclohexane. So its mechanism is, step 1 is the pi bond attacks the hydrogen, forming a carbonation, on the cyclopeia ring. And step 2 is iodine or iodide as to the carbonation. So the final product is iodoyocyclohexane. So that's all about hydrohalogenation alkene. Thank you.
Good day everyone, I am Syra Bactasa and today I am going to discuss the hydrohalogenations of alkynes. So what is hydrohalogenations of alkynes? It is an addition of alkynes with hydrogen halides or hydrohalogenation. When hydrogen halide is treated with alkynes or triple bond compounds, it results in the formations of gym halides. Gym halides are the compounds in which two halogens are attached to the same carbon atoms in a molecule. Alkynes are more reactive and better nucleophiles than alkenes. Similar mechanism as alkenes. Two addition, reaction, and the final product is the haloalkane with two halogens bonded to same carbon. We have seen that the electrophilic addition of hydrogen halides to alkenes produces alkyl halides according to Markovnikov's rule. Alkynes undergo hydrohalogenations following a similar pattern. The addition of one equivalent of HX produces a vinyl halide which is an alkene that is converted into a geminal dihalide upon the second electrophilic addition of HX. To distinguish geminal and vicinal, you can go with geminal as being jam on the one carbon. More scientifically, it comes from the Latin geminus, twin. The mechanism and radiochemistry of alkyne hydrohalogenation, like in alkenes, it starts with the addition of H plus to the pi bond, forming an sp hybridized vinyl cation. The more stable 2-carbocation is then attacked by the Cl forming a vinyl chloride. The resulting haloalkane is less reactive than the unsubstituted alkane since the electronegative halogen decreases the electron density of the double bond by the inductive effect. Therefore, the reaction can usually be stopped at this step if needed. Let's summarize the mechanism of the hydrohalogenations of alkynes. The second addition of the acid occurs starting by protonation of the vinyl halide. Two carbocations are possible here and each has an argument to be supported. On one hand, carbocation A is a secondary carbocation and from that perspective should be more stable than carbocation B. On the other hand, the positive charge on A is next to the more electronegative Cl atom and this is not a good combination. However, there is also the factor of resonance stabilizations which is only possible for the carbocation A. And this is the determining factor that favors the formations of carbocation A. Later on, we will also see how the resonance stabilizations determines the directing effect of halogens in electrophilic aromatic substitution. Notice also that in the second resonance structure, all the atoms have a complete octet which is one of the key factors for determining the resonance stability and major resonance contributor. After the second nucleophilic attack of the Cl, a geminal dihalide is formed. Looking at the overall addition of HX alkynes, we can see that it is a radioselective reaction of following Markovnikov's rule. Since first, the more substituted carbocation is formed and for the vinyl halide is a resonance stabilized carbocation is formed. The stereochemistry of alkyne hydrohalogenation. If an internal alkyne is used, there is no radiochemistry involved and a mixture of E and Z isomers is obtained. Just like for alkenes, anti-Markovnikov's additions of hydrogen bromide to alkynes can be achieved when the reaction is carried out in the presence of peroxides. Only HBr works for anti-Markovnikov's addition to terminal alkynes. E and Z alkenes are formed. The reaction goes by a free radical mechanism. Here are the examples. The reaction shows 1-butane reacting with 1 equivalent of HBr. This is an electrophilic addition reaction. The pi electrons
of the alkynes triple bond act as a nucleophile, attacking the electrophilic addition hydrogen of HBr. This leads to the formation of a carbocation intermediate on the more substituted carbon or Markovnikov's addition. The bromide ion then attacks this carbocation, resulting in the formation of 2-bromobute-2-ene. Because only one equivalent of HBr is used, the reaction stops at this stage. A second addition to form a geminal dibromide does not occur. The major product is the more stable E isomer. Next, this reaction involves the addition of two equivalents of HBr to one butane. The first equivalent adds according to Markovnikov's rule, yielding to bromobute-2-ene, as in part A. However, since two equivalents of HBr are present, a second addition occurs. This second addition is also Markovnikov's, adding another HBr molecule to the double bond of the intermediate to produce 2,2-dibromobutane. The final product is a geminal dibromide, meaning two bromine atoms are bonded to the same carbon atom. And the last one, the reaction shows an alkane reacting with excess HCl. The triple bond will undergo two successive additions of HCl. The first addition follows Markovnikov's rule, adding the hydrogen to the less substituted carbon of the triple bond, creating a vinyl halide intermediate. A second addition of HCl to this intermediate, again following Markovnikov's rule, will yield a geminal dichloride with both chlorine atoms on the same carbon. The presence of excess HCl ensures complete addition across both bonds of the original triple bond. Another example of hydrohalogenations of alkynes: 1-butane, 2-chloro-1-butene, 2,2-dichlorobutane, 2-butane, 2-bromo-2-butane, and 2,2-dibromobutane. And that's all. Thank you.
Polymerization of alkenes. Polymerization of alkenes is when small molecules called monomers link together to form a long chain called polymer. This is monomers. It undergoes the process of polymerization, and then the result is polymers. Think of it like stacking Lego blocks to build something big. In the case of alkenes, the double bond in their structure is what makes this possible. And then during the polymerization, first is the double bond breaks in each alkene molecules. Then the molecules join together like a chain, one after another. For example, we have here ethane, or the C2H4 molecules. This one. First is the double bond opens up or breaks in. Then each carbon can make a new bond. Then the molecules join to form polyethylene, which is used in plastic bags and bottles. So it forms like this, from monomer to polymer, or the ethane to polyethylene. It's just a matter of repeating the process over and over until you get a long sturdy chain. So that is the polymerization in alkenes.
So, hello everyone. My topic is all about alkane acid base reaction. So, before that, I'm gonna introduce myself, and my name is Abigail May Buka, Group 1. So, Alkane-based reaction involve terminal alkanes, which have acidic hydrogen due to their sp hybridized carbons. This higher S character makes them more electronegative, thus stabilizing the conjugate base form when the hydrogen is removed. The acidity of terminal alkane is essential for forming reactive intermediate used in organic synthesis. So let's think of an example. Okay, acetylene, which is a two-carbon alkane, also known as ethane, and we're reacting it with sodium amide. So first off, I've drawn out the structure of acetylene, also drawn our sodium amide in a bit more detail, recognizing that it is an ionic bond between sodium, which is toward the far left side of the periodic table, and the nitrogen is which is more farther toward the right. This difference means sodium has a positive charge, while nitrogen has a negative formal charge. The nitrogen with the negative formal charge is quiet and stable and very basic. Why it is basic? Why gani basic kayo ang nitrogen? Because it was stabilized itself by acting as a base. It is used its lone pair of electron to grab a proton. And when it does that, it becomes NH3, which is ammonia. Yes, ammonia, which is much more stable with no formal charge. Excuse me. In this reaction, the sodium amide acts as a base because it has the negative formal charge and a lone pair of electron, allowing it to act as a base. The acid in this reaction is the acetylene. Now, acetylene is not particularly acidic, but it is reactive enough to donate a proton. Its pKa is around 25 and so, which is significantly acidic compared to most hydrocarbons. The reaction mechanism involves the sodium amide's lone pair of electrons attacking and pulling away the proton from acetylene. We can represent this with an electron pushing arrow. When the proton is removed, the bond between carbon and hydrogen breaks, and when the pair of electrons from the carbon goes into the carbon. The product of this reaction are the conjugate base and conjugate acid. The conjugate base form is the acetylide anion, which is highly reactive and useful in further organic reaction. The conjugate acid is ammonia, NH3, which is stable due to the neutralization of the negative charge on nitrogen. It is important that throughout this whole process, the sodium cation acts as spectator ion. It presents but not actively participating in the reaction. Its role is to balance the charge of the acetylide anion that forms during the reaction. So that ends my topic, and I hope you understand